For this experiment, we're going to be looking at the preparation of a Grignard reagent and then its application in a carbonyl addition reaction. Now, when we think about preparing Grignard reagents, we've probably all seen in class the classical magnesium in diethyl ether here. But it may not be super intuitive why that's so important. Why do we specify the solvent there? Well, ether is actually very critical for this. We can't have a protic solvent, so something like ethanol or even something like dimethylformamide, which is a common solvent. We can't have anything protic because then as soon as we form the Grignard, it would be immediately destroyed by simply deprotonating the protic species and giving you just benzene as the product. And that would be, of course, useless. And it also can't be many aprotic polar solvents because often in those cases there's double or triple bonds. For example, acetone has a carbonyl. You certainly couldn't use acetone as the solvent for a Grignard reaction because it would simply react with the acetone as soon as you formed it. Or acetonitrile has a carbon-nitrogen triple bond that could be added to. Even something like DMSO has a sulfur-oxygen bond that could be added to. And so we generally cannot use polar solvents that would solubilize the Grignard reagent, but unfortunately would also react with it. And we can't use non-polar solvents such as hexanes, because in that case, the phenylmagnesium bromide, the Grignard reagent itself, which is essentially kind of almost like an ionic salt, here with a negatively charged carbon and then a positively charged magnesium, that would be insoluble and is insoluble in very nonpolar solvents such as hexanes. So you're left with ether and similar other ethers, something like THF, tetrahydrofuran is another ether. And it turns out that the lone pairs on the oxygen here are really critical in terms of coordinating to the magnesium and solubilizing that phenylmagnesium Grignard reagent. And so that's one reason why we see ether here so commonly. Now what we're going to do is we're going to take some magnesium turnings, common magnesium ribbon, polish those up to remove any surface oxide, because often magnesium, when you get a magnesium ribbon, it's often not just magnesium solid, which is what we would like, but the surface is covered with a layer of magnesium oxide, a passivated layer, just from reaction with oxygen in the air, and this renders the surface fairly non-reactive. And so this would be a slow process to form the Grignard reagent. Often we will also add a small crystal of iodine, because iodine also helps to react with the magnesium oxide and sort of clean that surface so that it's able to react with the Grignard, with the aryl halide to produce the Grignard reagent. Now, after we've got the Grignard reagent, what we're going to do is we will then add in benzophenone. Here, it's simply a ketone reagent. My Grignard reagent will attack in a nucleophilic manner here to kick this up, and we'll initially get to a magnesium alkoxide species here. And then finally, once we've got this kind of salt material here, which will be somewhat insoluble actually in the ether material, then we will add HCl at the very end of the reaction, kind of a dilute 3 molar HCl at the end of the reaction to hydrolyze off this salt here and simply protonate the alkoxide to produce our final triphenylmethanol as a white solid. Now, we also have to pay attention in this reaction. Grignard reactions, as we've already kind of mentioned, they're very susceptible to protic species. So this needs to be very water and moisture free, because otherwise water would essentially simply quench the Grignard reagent. But it's also important to try to keep this reaction as oxygen free as possible. Now, we're not going to be able to do this entirely, but the reason why oxygen is an issue here is that oxygen will react with the Grignard reagent and essentially cause radical intermediates. So oxygen kind of cleaves off, essentially steals one electron from this, and you end up getting to these kind of aryl radical intermediates here, which if I've got another one of those, let's say I've got 2 of these can dimerize to give me what's known as biphenyl, simply 2 phenyl rings linked together. This is an undesired byproduct that we do observe in the reaction. And we can remove it at the end here by, from its a crude mixture here with the desired triphenylmethanol. We can remove that by washing with hexanes, because biphenyl is very nonpolar and is soluble in hexanes. But triphenylmethanol, because of that alcohol group there, is more polar and as a result is not soluble in hexanes. And so that will allow us to separate that out. And so hopefully this experiment will serve as a good introduction to the techniques required to prepare a Grignard reagent and apply it in a chemical reaction. So with that in mind, let's go get our PPE on and set up this Grignard reagent. And before setting up a Grignard reaction, we would normally have dried our glassware ahead of time by leaving it several hours or even overnight in a hot oven to remove any residual water moisture that's on the glass, since Grignard reactions are very sensitive to water content that can destroy the Grignard. However, let's say that we forgot to do this, or that we just decided this morning to set up a Grignard reaction. Here we can still dry our glassware in a much faster manner, which I'm going to demonstrate using a process known as flame drying. So here I have chosen a small round bottom flask rather than a conical vial for this reaction, and I've got a small Teflon coated stir bar here. I'll simply add that into my round bottom flask. And now this has just been taken from a drawer. It's got water vapor on it just from regular exposure to fairly humid air here in the atmosphere or in the lab. And the way that I'll get rid of that water moisture and make sure that my glassware is rigorously dry is by using the Bunsen burner. So I'll take it, I'll turn the Bunsen burner on, I'll take my flask or my round bottom flask here and just sort of use that flame to drive off the water vapor. You'll see it visibly as water vapor leaving or climbing up the flask as I heat it with the Bunsen burner. Now, it doesn't take very long at all. All I want to use is that flame just to drive off that water. Once it's gone, then I'll take that round bottom flask over to the hood and cool it under a stream of inert gas. So in this case, nitrogen, just to let it cool so that it won't condense or recondense water vapor from the air as it's cooling. So here I'll demonstrate that process. We'll turn the Bunsen burner on. You can hear the gas hiss. Light that with the striker. You'll see I have a nice blue cone there, a hot flame. And so then I'm going to grab my round bottom flask. Now with these large tongs, grabbing around the neck may work well, and I seem to have a fairly solid grip, but sometimes it's a little bit shaky or rocky, and I don't want that when I'm flame drying. I want to have a really good firm hold. So also with these small vials, sometimes grabbing just inside the neck will also work well, and I'll do that here. So look carefully for that water vapor. Oop, there you see it around the edges. Now I'm just going to rotate the vial or the flask just to drive that out. I'm going to then dry the neck real quick on both sides, and I'm done. That's it. I don't need to leave it in the flask, or I don't need to leave it in the flame long at all. I simply want to drive off that water. And now that I have, I will take this hot round bottom over to the hood and cool it under a stream of nitrogen. So I've got my hot round bottom here. Bring it over, clamp it carefully in the hood. It doesn't need to be above a stir plate, just so that it stays kind of steady, doesn't fall over. And then I've got a nitrogen line right here connected to a manifold. I'll simply place this inside here, just sort of let it rest and make sure that I've got a decent stream of nitrogen flowing, and then just let that cool. I could alternatively pop a septum onto here and then put a nitrogen needle down through the septum and another vent needle out to allow the system to cool under flowing nitrogen. But here, just having it open like this should be sufficient until it cools. So now that our round bottom flask here has cooled, it's time to weigh out our magnesium ribbon to begin getting ready for preparing the Grignard reagent. So here I've got some magnesium ribbon. Just grab out a piece. We're going to do this. Ooh, looks like I got two.
We're going to do this on a slightly larger scale than the pre-lab reading. We're going to do it on double the scale. So rather than 18 milligrams of magnesium, I need 36. So initially, I'm just going to take this and I'll take a piece of wave paper and fold it like I normally do. Let's just get a rough mass, see where we're at approximately here. Just tear this. See how much we've got there. So we've got quite a bit, 45 milligrams roughly of magnesium. We certainly don't need that much, but good to make sure we've got a large enough piece of ribbon to begin with. We can trim that down. I'm going to take this other piece and put it away. So what we will do is we'll use the scissors to cut this piece of ribbon down some. But before I do, you may not be able to see very well on here, but there's little bits of discoloration, sometimes little bits of white on this ribbon. It actually looks pretty shiny, but I want to make sure that the surface of the magnesium ribbon is really clean from any surface oxides. So magnesium will react with oxygen in the air to form magnesium oxide, which creates kind of a pale white passivation layer over the active magnesium metal, and that'll make this reaction really slow because that magnesium oxide doesn't react. And so what I want to do then is I want to try to clean some of that off. So I could do that with multiple different ways. I could use actually dipping it in some acids, so in like HCl solution could work here. I could take some sandpaper. In this case, I've got some steel wool. Just going to pull out a small bundle of steel wool here. And just try to polish my ribbon in some way with that steel wool. Might have to really scrub at it here, trying to remove off that surface oxide layer. Basically, I just want to polish that surface as much as possible. And once I finish polishing, then I'll trim it with the scissors down to get me approximately the mass that I need. Now have kind of a nice shiny magnesium ribbon. And so we'll take this now and trim it. I had approximately 45 milligrams. You'll see I've shaved off a couple milligrams just by cleaning it. I'm going to trim that down just a little bit. I want to get to about 36. Okay, so I undershot a little bit. I need another small piece of 32. I just need a little bit more. Just cut a very small piece here. Ooh. Drop that small piece on. There we are. 36 milligrams. Ooh, perhaps not. Maybe we need just a teeny bit more. 35. That seems pretty sufficient right there. So we'll actually just take that amount right there and then add it into our round bottom flask. Now, for stirring purposes, just to make some of the actual physical process of initiating the Grignard and performing the Grignard, I'm actually going to take this large piece of magnesium ribbon and simply chop it up into small chunks. That should make it a little bit easier for the reaction to initiate and then sort of consume that nitrogen, or that magnesium. So I'll just carefully chop this to a lot of little small pieces that I can then add into the round bottom flask. Now, even though I've polished the surface of the magnesium, I'd like to really make sure that the initiation takes place and that the magnesium is really active. And so to help with this, I can take a small crystal of iodine, not much at all, but just a small amount, generally a single crystal or two, and add that in to the flask. We've got just a little bit there. That iodine should help activate the magnesium surface and then should make initiation of the Grignard reagent much faster. I'll now clamp the flask above the stir plate. And have it set over a sand bath so that we can do heating later to help induce the Grignard. I'll add 200 microliters of dry diethyl ether to this. So that we have a very small amount of solvent in there. And I will cap the system with a septum cap. Now, the pre-lab video may not have explained this very well, but oxygen, in addition to water, is really the enemy of a successful Grignard reaction. Oxygen will cause the Grignard reagent to homolyze and give you free radicals that then can dimerize and undergo other undesired reactions. So here what we'll do before we even add the aryl bromide, what we want to do is just purge the atmosphere with an inert gas such as argon. So here I have an argon balloon. I'm simply going to take this balloon here and put it down through the septum. So we'll kind of carefully push that down through the septum, ideally through the center, into the headspace. And then I'll add a vent needle here just to allow air to escape. So I'll kind of push that there. And then I'll push my argon balloon all the way down to the bottom just to bubble some argon gas through the little bit of ether that's down there in solution. And so then we'll let that sit for a while and purge the headspace of the flask with argon. And then we'll actually just leave it in there and add the reagents under an argon atmosphere. And we'll remove the vent needle here in a few minutes. To add to the magnesium turnings, I'll take 152 microliters of bromobenzene. And then we'll add 800 microliters of dry ether to the reaction. Not to the reaction, but just to the vial. sort of swirl this solution, and then we can suck this solution up with a 1 milliliter syringe and needle, and then it will be all set to add to the magnesium turnings. Add another 600 microliters of diethyl ether to rinse the bromobenzene vial and add that to the reaction. Heat the reaction gently for 15 minutes, setting the hot plate not much more than 50 degrees since ether is low boiling. Ideally, the iodine color there that is kind of this sort of brownish or yellowish should disappear as the Grignard reaction is initiated and begins to consume the magnesium turnings. We now weigh out approximately 210 milligrams of benzophenone and dissolve that in ether, and then we will add this to the prepared Grignard solution. We'll now add approximately 600 microliters of diethyl ether to the benzophenone, dissolve the solid, and then we can add that solution slowly to our prepared Grignard reagent. Now that, as far as we can tell, the vast majority of the magnesium has been consumed and the iodine color is now gone, we have kind of a grayish, somewhat cloudy Grignard reagent. We are now all set to add the benzophenone solution. So we'll do that slowly via syringe through the septum. And then we'll add an additional 600 microliters of just ether wash to carry forward any benzophenone solution that we leave behind. That beautiful bright pink color comes from the alkoxide intermediate after the Grignard has added into the benzophenone. So this is a really good positive sign that this reaction has worked, that we formed a Grignard reagent, and now we have that beautiful pink color as we begin to add the benzophenone solution. We've rinsed the benzophenone vial, and we'll now add that extra ether rinse just to carry forward any benzophenone left behind. This we can add a little bit more quickly to the solution. Eventually that pink alkoxide color goes away. We'll let this stir for a couple minutes and then we'll cool to room temperature and perform the isolation. Now that the reaction is finished, we can remove the argon balloon carefully, vent that into the hood, stop the stirring, and then we'll remove the septum here in order to begin to work up the reaction. So let's just see what this product looks like here. It's kind of a very frothy white kind of precipitate, bunch of magnesium salts there. I'm going to remove the septum cap. Actually clamp this back into the system here. And then begin to hydrolyze that magnesium alkoxide using the addition of 3 molar HCl until the solution is test acidic. I'll turn the stirring back on so that that can help to dissolve the salts as I add aqueous solution here. Do this very kind of carefully. You see some frothing there as that kind of all begins to dissolve. So the salts sort of react with the HCl, the protonate, and then it begins to form kind of a biphasic mixture here. We might have a little evaporation of the ether. You can always add some more ether in a little bit to this. You can see that not quite all of the solution is dissolving, but most of that is beginning to dissolve. We can test the acidity of the resulting solution using some blue litmus paper here and a stir rod. Stir rod can also be used to help break up any salt, so it looks like most of that solid material is now broken up. I can take a glass stir rod, just sort of dip in here, make sure there's no solid material other than the stir bar. Test that on the litmus paper here. You can see that is pink, so we definitely have an acidic solution there. So we should have, at this point, hydrolyzed all of that magnesium alkoxide. We should be able to sort of let the 2 layers settle. Turn the stirring off here. It's as though we might have a very small piece, something right there. Looks like it's all dissolved at this point. Now, if we need to add more ether, we can. We should be able to now have 2 layers, an ether layer and an aqueous layer. We should be able to then kind of pull off the ether layer and then extract the resulting aqueous solution several times with additional ether. So here we seem to have all of the solid alkoxide salts dissolved. We don't really seem to have two layers very easily separated here. It seems mostly to be kind of a cloudy single phase solution. So what we're going to do is we're going to transfer the solution into a centrifuge tube. So take the centrifuge tube, transfer all of the solution there, add more ether, and then extract the solution essentially several times with ether to ideally remove our product and leave behind the inorganic salts in the aqueous layer. Now you can actually see a little bit better that there are actually two layers here. It's difficult to see in the round bottom flask, but there are actually two layers here. A top kind of colored yellow ether layer, and then a lower aqueous layer that's kind of cloudy. So we'll start by separating that ether layer out, and then we'll extract the remaining aqueous layer with several portions of diethyl ether. So we'll begin by removing the ether layer from the reaction here and placing it into another centrifuge tube. And then we'll extract the aqueous layer with 1 ml portions of additional diethyl ether. That's sufficient for now. Now we'll begin the extraction. So you'll notice that the solution of ether after the extraction is cloudy. This is due to the presence of trace amounts of the acidic aqueous solution remaining in the ether. Primarily from that very first removal, there was quite a bit of residual acidic solution remaining. And so to remove that, we will actually extract the aqueous solution once with some cold, just distilled water. We now dry the solution with solid sodium sulfate. And we'll let this sit for a few minutes to absorb any residual water in the solution. Weigh a clean round bottom for product isolation. Now we can transfer the dried ether layer into clean weighed or tiered round bottom flask. To do this, what we'll do is we'll remove the centrifuge tube with the dried ether, set that simply here in the vial that has also the aqueous extracts. We'll clamp the round bottom into place, simply to keep it from falling over. Take a funnel right here, pack some cotton in simply to catch any solid drying agent. Place that down into the round bottom flask. Swirl the solution with ether and the solid drying agent. Dump that down in. Mostly that filters through, but what we'll do is we really want to make sure that we don't lose very much product at all. So we'll take some ether. We'll grab some extra ether and rinse the drying agent, rinse the cotton, rinse the funnel, and rinse the original centrifuge tube. We can now road vap off the ether to leave us with a crude product, which we can then purify further. We can now get a crude mass for our crude product. The crude triphenylmethanol that we have right now, we could certainly get an NMR and a melting point for, but we would notice significant impurities because one of the byproducts of this Grignard reaction is homocoupling of the Grignard reagent to produce biphenyl. Now, we can remove that biphenyl here from the crude product by a process known as trituration. So biphenyl is very nonpolar and should be soluble in hexanes, whereas triphenylmethanol, although still fairly nonpolar, that alcohol group renders it significantly more polar than biphenyl, and so triphenylmethanol is insoluble in hexanes. And so if we simply take this kind of crude solid
material and add in some hexanes and simply kind of scrape up the solid material so that it's suspended in solution and the biphenyl byproduct has a chance to dissolve, then leaving behind the insoluble triphenylmethanol product, we can then isolate our triphenylmethanol by triturating a couple times here with hexanes. So I'll demonstrate that for you. I have a small Erlenmeyer where we will pour off or decant the hexanes after we've added them. I have here a beaker that has some hexanes. And so I will simply take some hexanes in a pasture pipette, add it into the crude product a couple times, say 3 pipettefuls. You may notice very minor changes in the appearance of the round bottom. Some material did actually dissolve, which is a good thing. We want the biphenyl to dissolve. But to help that, what I'm going to do is I'm going to go down with a spatula here. And I'm actually going to go down and start to scrape the solid here so that it has a chance to dissolve any of the biphenyl products, and it'll leave you kind of this cloudy suspension, leaving the triphenylmethanol material undissolved, but the biphenyl has a chance to dissolve. So here, I can try to get some of this stuff up on the walls by bending my spatula a little bit and reaching up there. I've bent my spatula some so that I can reach this stuff up on the walls a little bit easier. Kind of make sure this all gets a chance to interact with the hexanes. Swirl that all up. And you'll notice that I have pretty hefty suspension there of material that is undissolved, so there's precipitated material down at the bottom. And then there is the hexanes layer. Now, what I can do here, kind of as a rough process, is just to very carefully decant or just pour off that hexanes layer. Now, if I'm just careful not to pour any of the solid material and lose it that way, then I don't necessarily have to pour all of the hexanes right away. I can simply pour the vast majority of the hexanes off, add more hexanes in, triturate again, and then decant off the majority of that hexanes, maybe do it a third time, and then very carefully sort of remove the residual, decant off the hexanes, and then residual hexanes we can simply take back over to the rotary evaporator and remove there. So we'll decant this very carefully. I could also potentially remove this with a pasture pipette. Simply want to make sure that I don't lose any or very little of my solid material. So there I've removed the vast majority of the hexanes. I'm going to add more hexanes in and triturate again. So there we are, left with just a very small amount, just trace hexanes left in the vial. We'll take this back to the rotovap and pull off those hexanes for a while to leave it go to dryness. And then this should be our purified triphenylmethanol. We can get a final mass for it and get IR and NMR spectroscopy. Let's go get the final product mass.